So we're going to look at Bayesian optimization today. So Bayesian optimization is an interesting or very important application of Gaussian processes to some problems that we actually work with every day. And I'm going to give you a little bit of like also background reading material. So these tutorials. So the first one is a tutorial that it's been living on archive for 10 years. So, sorry, 8 years. So that one is actually really nice to read, and the journal article down here is also written in a way that it is of a tutorial style. So if you want to have a perspective or wider perspective on Bayesian optimization, and want to read an actual document and not the slides, I can recommend both of these papers, worthwhile reading. So when we talk about Bayesian optimization, we also need to talk about meta challenges that we have in machine learning. So let's talk about meta challenges in machine learning. So as you know, machine learning models are getting more and more complicated. So if you look, for example, at deep neural networks, you have a lot of parameters sitting there. And that means they're also not particularly interpretable, or you cannot, it's very difficult to understand what each parameter does. Then we also look at optimization methods for these machine learning models, these complicated machine learning models. And the optimization problems we are looking at are typically non-convex. And because of mini-batching, we also use stochastic optimization methods. But all of these optimization methods also have parameters that need to be tuned. We call them now meta parameters because they don't directly influence the machine learning model, but they influence more the way we optimize the models. So if we look, for example, at learning rates or momentum parameters. So one of the challenges that we have in machine learning is that because everything is very complicated, it is also very difficult to reproduce results and apply modern machine learning techniques to reproduce results that other people have reported. So we are going to look today at a way to automatically select critical meta parameters, such as learning rates, just as a higher level example. And there is a field that's called automated machine learning that is looking at exactly this kind of problem, but we are going to look at a subset of automated machine learning, which is Bayesian optimization. I want to give you maybe some more ideas of like what kind of problems we could theoretically be solving. So for example, if we look at deep neural networks, right? So when they are well tuned, they can be super successful for object identification, speech recognition, computational biology, and a lot of other problems, right? So I'm sure you have worked with deep networks quite a bit in the last couple of months. There's also lots of money involved. So Google, Facebook, Amazon, Microsoft, Twitter, everyone is putting money into this. But one of the tricky things is when we work with deep networks, and you must have discovered this already, is that we have a lot of choices that we need to make. We have to decide, for example, on the number of layers, whether we want to do weight regularization or what kind of weight regularization we want to do, the layer size, what nonlinearities we want to use, batch size, the learning rate schedule, again, in the context of optimization, stopping conditions, all these kind of things we have to make decisions on. So somebody is asking, what is a meta parameter? So meta parameters are parameters that do not directly control the distribution of the data. So the parameters of the model, for example, in a neural network, we have weights and biases. So these are direct parameters. But for example, if we choose the layers, the number of layers in the model, that is a meta parameter. Yeah, we can think of this maybe as a hyperparameter, right? So it indirectly controls the data, but not directly. So directly controlling the data distribution would be the weights and biases in the neural network. But maybe if we think about what kind of nonlinearities we choose, we use a value or a tanh or sigmoid, that is a meta choice, a higher level choice. Different example is, so that was an example for deep neural networks, but we can also look at an example of an application where we use latent Dirichlet allocation for topic modeling. So when we do LDA, we have to tune the parameters in LDA. For example, setting Dirichlet parameters or the number of topics we have to define, learning rate schedule, batch size, vocabulary size, all these kind of things are pretty difficult to set. But if we set them well, then we can get really good empirical results on topic modeling with latent Dirichlet allocation. But again, so the hyperparameters in here or the meta parameters are very difficult to set. So it would be great to have a mechanism that allows us to automate setting these hyperparameters. And maybe a third example I would like to give is DNA sequences, so classification of DNA sequences. So if we wanted to predict which DNA sequences will bind with which proteins, we could use something that is related to a special type of support vector machine. So there's a model called the latent structural support vector machine that does predict exactly these kind of things. So it doesn't really matter how this thing works, but there are also hyperparameters involved. So similar to another normal support vector machine, we have a margin or a slack parameter. Here we have additional like entropy parameter, and we also need to think about convergence criteria. So these are things that we need to set when we work with more complicated models on more interesting problems that we want to solve. And if we want to search for good hyperparameters or metaparameters, then we also need to define an objective function that evaluates the quality of these hyperparameters. Yeah, so similar to what we had in linear regression, we looked at RMSE values or log predictive densities. We could use cross-validation to measure the parameter quality. We can use cross-validation to get an idea of like what the generalization performance is. And then we can use standard search procedures for these hyperparameters. So either we do this manually, so we try a hyperparameter, we see what, let's just fix on a learning rate. We try a learning rate for a deep network. Then we train our deep network with that learning rate or learning rate initialization. And then we would get a result at some point. And then we say, okay, if we get this result, let's maybe try a slightly different learning rate. So make it a little bit bigger, a little bit smaller, right? So this is what I mean by manual tuning. We can also do grid search, where we just try a bunch of learning rates between whatever 10 to the minus 4 and 10 to the minus 2. We can do random search. So random search would be, so let's say if we wanted to do grid search, we would have just a regular grid in some space. Random search just uniformly at random samples learning rates within an interval. And that is also super simple, but it works surprisingly well. And there's also black magic. So people are asking, like, what is black magic? So black magic is somebody just knows what the right learning rate is, or ballpark. What is a good learning rate for training a deep network? Well, it starts with 10 to the minus 3, something like this. Somebody knows what a good number is, and that's kind of like black magic, or maybe experience. There's a lot of like background knowledge that comes in here. So somebody's asking computational cost in the choice of these search procedures. So the computation cost for manual tuning is zero, because the manual tuning runs in your brain. So that is your brain power comes in here. Grid search is super easy, right? So you just need to define a grid. I mean, evaluating the quality of these parameters is expensive, right? So if you have to train a neural network, maybe for a couple of weeks, then every evaluation of the quality of these learning rate parameters costs you a couple of weeks compute time. But setting the parameters is very cheap. So a lot of things are also problematic with this. Evaluating the quality of the objective may be very expensive. That could mean like we have to invest a lot of time or money For example, imagine we would need to run a GPU or TPU cluster for 2 weeks to evaluate what the quality of one of these hyperparameters is. Then we have to pay both money and time to get this evaluation. It would require a lot of training cycles, and our results would possibly be noisy because of the stochasticity of the optimization problem. But the other thing is that even if we have a fully deterministic optimizer, it may be we may only be able to observe noisy measurements of the quality of our hyperparameters. Okay, and this is kind of like where Bayesian optimization kicks in, or where we want to start using Bayesian optimization. So the setting that we are looking at is we want to globally optimize a black box objective that is expensive to evaluate. And so black box is that expression. Have you heard of a black box before? So let's assume we have parameters X, and we're going to feed them into a machine learning algorithm, and then we measure an outcome. Let's say the cross-validation error, for example. But we don't really know how the inputs X and the cross-validation error are related to each other. So let's say if we define this to be f of X, we would not be able to write down what f is. It's too complicated. So this thing now is called a black box because we don't have much, or we don't have any information of how the internals of this black box work. But what we can do is we can query the black box using a parameter X, and we can observe an outcome, f of X. So that is what I mean by black box.
So I've been wondering to ask this question with regards to the black box. So most often we read that neural network is actually a black box. I still don't get why we classify it as a black box, because given that we know that, okay, from the first, when we pick the inputs, it picks some certain inputs, then we pass it through the layers, then you have activation functions that goes on through each of the layers. So why do we still call the neural network a black box? I don't know if you could just give me a clearer explanation.
Yes. So I would actually not call a neural network a black box. We know the internal structure of the neural network in this case. So if we talk about how inputs are being mapped to outputs, whether that is a class label or whether we use a neural network for regression, doesn't matter. We know exactly how this works, because otherwise we couldn't do backprop. So we can write down a function that tells us how this works. Whether that is interpretable is a different question. And so some people say this is a black box in that sense, because I don't understand how it works. But what I'm talking about is more like, how does a learning rate schedule influence the cross-validation error? That is what is very difficult to understand. And then if you just take the mapping from learning rate schedule to cross-validation error, that is what I call a black box, because I could not write down the functional relationship between a cross-validation error and the learning rate schedule. Okay, so here the key idea is that if we cannot observe this kind of like black box, let's try to model it. Yeah, so let's try to model the relationship between the hyperparameters or metaparameters that we pass in and the things that we observe, such as the cross-validation error. And we're going to use a probabilistic model to describe that functional relationship. Yeah, so we approximate the black box using a probabilistic model, and we use the outcomes of past experiments as training data. Yeah, so we can query the black box, we observe something, we query the black box again, we observe something else, and you can use this as training data for a supervised learning problem. This kind of like proxy model is much cheaper to evaluate than the original objective function. So imagine again that you have to wait for 2 weeks wait for an outcome of your experiment. For example, if you have to train a really big neural network and then run cross-validation on it. But if we had a proxy model, we can just evaluate the functional relationship without actually training or using the deep network to get true observed function values. So we have a mapping here that goes from x to f of x. Let's assume we have our first experiments where we use x1 as our first input. And now we wait for 2 weeks and we get one observation. And now we're trying something else. So here's x2, the second experiment, and we get a different observation. We wait for another 2 weeks. And we're going to try again with x3, and we have another value after 2 weeks. Now we have waited for 6 weeks, or we can parallelize, so we wait 2 weeks with 3 TPU clusters. And the question now is, how can we efficiently evaluate f of x at many points? So proxy, sometimes maybe it's just like an approximate model, or sometimes also called a surrogate model. Yeah, so it's a model that emulates the ground truth or approximates the ground truth. We have seen these kind of problems already this week where we had a bunch of points or function evaluations, and we were then fitting functions or regression functions to this kind of training data. This week we looked at, for example, at a Gaussian process, and a Gaussian process would maybe fit something that looks approximately like this, and we would get maybe some sort of like error bars that may look like this. But so we have already looked at problems which look very similar. It's just here we have an active process of generating these training data, whereas in the examples we looked at this week, the training data was given. Question? Somebody's having a question? Okay, not. Yeah, so this is kind of like the setting that we will be looking at. So, and this kind of like approximate model is much cheaper to evaluate than the original objective, because we don't have to wait for 2 weeks to get a function evaluation. So now, if we had now this approximate model, if that model that is relatively cheap to evaluate, because we just wait for like a few milliseconds or seconds to evaluate this function, if that is very close to the true function, then we can just say, why don't we just optimize this approximate function, this proxy function, and then find the optimal parameters for our deep network. So for example, the learning rate. Yeah, so it's about finding optimal parameters for our expensive function by not using the expensive function. And what kind of like ties this back to what we've done this week is that the standard approximate or proxy model that is being used in Bayesian optimization is a Gaussian process. Just like to now formalize this a little bit more, the setting that we had is we are interested in finding a global minimum of an objective function g. Yeah, so we want to find the argmin of g of x, and that is the optimal parameter setting that we would be interested in. So think of this as the optimal learning rate for evaluating the cross-validation error of a deep network. And so g of x would be the cross-validation error of a deep network for a particular learning rate, for example. So what we can do is we can evaluate this objective pointwise. Yeah, so if we can pass in a parameter x, we can evaluate this, but we do not have we don't have an easy functional form or gradients and observations can also be noisy. We are interested in finding the global optimum if possible. Normally, right, so if you run gradient descent, you would end up in a local optimum. We are interested in finding a global optimum. So next question is also very good. So do we optimize the proxy model each time we make a new observation? Quick answer is yes. And we're going to get to this probably on the next slide. And it is cheap. So the proxy model is cheap because it's very easy to evaluate, or cheap to evaluate in terms of like compute resources and time compared to evaluating the true objective function. So again, if you imagine that you have to train a deep network for a couple of days, you have to wait for a couple of days to evaluate the quality of one learning rate. And so these are exactly the kind of like settings that we have, right? We have some hyperparameters or meta-parameters of our learning algorithms, which are here on the x-axis. And then we have observations of our objective function g of x, for example, the cross-validation error. And now we want to find out what are the parameters x which give us the smallest cross-validation error. So we want to minimize g of x, but we only have some observations. So what we could do is we can find now a regression function. So we can connect all of these dots and try to find the minimum of that regression function. All right, so here are the key steps of Bayesian optimization. So to avoid evaluating this expensive function g an excessive number of times, we approximate g using a proxy function g tilde, which is cheap to evaluate. Then we find a global optimum of g tilde x of x star of this proxy function. And then we take this x star value that we found by optimizing g tilde to now evaluate the true objective at this point. If we were to optimize g directly, and let's say we would run gradient descent, we have to evaluate g many, many times to actually get to a local optimum, and we would need to have gradients. Whereas here we take the kind of like the optimization away from g and use g tilde to run this optimization. We can evaluate g tilde many times. And once we find an optimizer, x star of g tilde, we can now evaluate the true objective function at x star. So all of this requires evaluating g a single time, which is in this third bullet point here. We're going to repeat this with more details a bit later, but this is at a very high level. That is the key idea. So this works well if g tilde is approximately equal to g, because then we would just have a cheap version of g.
The proxy function, is it a convex function?
No.
So how are you sure that you find the global optimum?
So that's also a good question. So we need to run global optimizers to find the optimum of g tilde. So that is it's also a difficult optimization problem, but we are allowed to evaluate g tilde at many points. So, and then normally we would need to repeat this cycle, because without any data or with very little data, g tilde will not be similar to g. And so once we have now evaluated g, then we update the model, the proxy model g tilde, and then over time it becomes better. And maybe I'll give you a picture illustration of how this works. Imagine our true objective is this blue line. Yeah, so we want to find a global optimum or minimum of g of theta. So that's somewhere around here. Now we have one observation of what g is at this particular point, and we're going to fit a Gaussian process to this with one training point. So the Gaussian process with one training point is illustrated here. So you know the posterior mean function is the black line, and the shaded areas correspond to the uncertainty. what we're going to optimize now, or what we're going to use now, is we're going to look not only at the global minimum of the mean function, but we're looking at the minimum of the mean function minus 2 times the standard deviation. And that would correspond to the minimum of the gray shaded area. That is the function we optimize. So basically the function that we want to optimize looks like goes up here. It has this like mountain here and then goes back down. We want to find the minimum of this. And the minimum is now here at theta equals -5. So that's what the Gaussian process tells us. That's the minimum of the shaded area. And so this is now where we evaluate the blue function next. So now we're going to evaluate the blue function next at this point. So that's now the observation that we have, and we update our Gaussian process model. Now we're going to go back again and say, okay, where is the minimum of the of the shaded area? And so now the minimum of the shaded area is at theta equals 5. Now we're going to evaluate the blue function again at theta equals 5 and update the Gaussian process. And then we kind of like repeat this. We're going to look again at the minimum of the shaded area, which is now here, and evaluate the blue function, so the expensive function, where the minimum of the proxy model is. And we keep doing this, and you can see that after a few iterations, the Gaussian process is a relatively good approximation to the blue function. So that already looks relatively good. And so we keep doing this now. And now we are basically at the point where we say, okay, we just keep repeating, evaluating at the same point. And we found the global minimum of the blue function by evaluating the blue function only a few times, let's say 10 times or so. The Gaussian process model is not great everywhere, but in these areas over here on the right-hand side, we're not really interested in having a high-quality approximation because the function values are just too bad. And so we are interested in minimizing g of theta. And so that means we need to have a relatively good approximation of g of theta, where g of theta is small. Whereas g of theta has high values, like here, we don't need a good approximation of the good proxy model. So that is the idea of how Bayesian optimization with Gaussian processes works, like in pictures. So in the second part today, we're going to look at how to choose the next point to evaluate the true objective function. So where do we find these x star values from? If we look at the proxy, in our case, the Gaussian process, and what we're going to look at is something called an acquisition function. The acquisition function tells us where to evaluate the true function, the true objective function next. And so here's again, one of the settings that we're looking at. We're interested in finding a global optimum of the true objective function, and we need to use a Gaussian process that also gets us out of local optima. So what we're going to do here is we need to be able to extrapolate from knowledge that we have already collected, which is represented by these data points, by these crosses. So that is something that we have seen before. And a GP allows us to do exactly this. So because the GP gives us closed form expression for means and variances, we can use this to trade off exploration and exploitation. So exploration means we are looking for places where the Gaussian process has high variance or high uncertainty. For example, in this picture, that would be some here on the right-hand side, and maybe also somewhere here where we don't have much data. But we can also exploit what we already know. So if we are interested in minimizing our true objective function that we have evaluated at a few points, then the posterior mean is an indicator where we can look. So if we look at places with low posterior mean, then we can exploit that knowledge. So ignoring all the uncertainty that comes with the Gaussian process, if we just look at the mean, we can exploit the knowledge of places where the mean is low. So it's an indicator where the true function is also low. So these kind of things that, so exploration, like look at places with high uncertainty, and exploitation, look at places that have a low mean, that is something that we need to be trading off. And that is exactly where these acquisition functions come into place. So acquisition function, we're going to denote them by alpha. They trade off exploration, exploitation for our proxy optimization. So here's how this entire thing now works or Bayesian optimization works. So assuming we have an initial data set of evaluations of the true objective function and corresponding input parameter or input values, so x0 and y0, then using this data set, we update our Gaussian process, or we train our Gaussian process. Then we select the next values or next parameters xt by optimizing this acquisition function. We evaluate our true objective, so now g, at this corresponding point. And then we augment our data set by xt and the noisy observations of g of xt. So yt could be g of xt plus epsilon, for example. So now we have an augmented data set. Now we update our Gaussian process using this bigger data set. We then evaluate again or optimize the acquisition function again. And then it will tell us again where to evaluate our true objective function at a next. So that would be the next xt. And we again augment the corresponding data set. And then we keep going through this. And at some point we decide to stop. And then we return the best input in the data set that we have found, which would be the x star that gives us the minimum observed function value. Okay, so now let's maybe go through this example. We've run 4 experiments with our deep network, and we have 4 function evaluations. So now we're going to train a Gaussian process on these 4 data points, and now we're going to sample a function from this Gaussian process. For example, this one here. So what we could do now is we could now find the local, or let's say the global minimum of this blue function. And then we would maybe choose this point here. We could also sample another function, the orange one here, and we keep maybe sampling a lot of functions, and we could look at every single function where every single function has its minimum. What we can also then do is so if we sample many times, we would get like these many samples here. And then we could look at which function values are actually better than the best function value we have seen before. So if we look at this example here, the best function value we have seen here is this cross. Now we have a few function values in this blue line which are better, which are around in this area here. In the yellow function, we would have many function values in this area here where the corresponding function values are lower than the best point that we have found so far. And we can do this now for every function. So that one, if we sample 1,000 functions from our posterior GP, and the black line is the function value that was minimum so far, we can now count pretty much or draw a graph of what is the best thing or the best places to evaluate, so that with a high probability, we get lower function values. So that would be the graph here at the bottom. So the probability of getting a lower function value if we evaluate, for example, at around 0 is maybe 0.18. So 18% probability of getting a better function value if we were to evaluate the true objective function at this point. The lower panel here is called the expected improvement over the best solution so far. So that's how much better is our function value expected to be compared to the function value that we have seen so far. And so now we use now the mean, the posterior mean, and the posterior covariance, or the posterior covariance function, to draw these samples from a Gaussian process to compute the expected improvement over the function value. And now we're going to use this function here to determine where to evaluate next. So this function here at the bottom is an example of one of these acquisition functions, which is the expected improvement over the best solution so far. And then we maximize this acquisition function, or this expected improvement, and we'll find an optimal value to choose, which is a little bit smaller than 0. And that would be the next point where we would evaluate our true objective function. So that's an example of one of these alpha functions that I mentioned earlier. I want to give you an example of maybe 3 acquisition functions. Setting here is we have a d-dimensional input parameter, x, and we have a Gaussian process posterior that gives us a predictive mean mu of x and a variance sigma squared of x. So now we also have the best input value. So that would be the input value of the best function value that we have seen so far. So that would be around here in the previous example. And we can define gamma of x as g of x best minus mu of x divided by sigma of x. What this does is, you've probably seen this similar to batch normalization. It centers our values, and if you divide by the standard deviation, then effectively, if you look at the distribution of these gamma of x values, you will get a standard normal distribution. So with this definition, we can define 3 acquisition functions. So one is called the probability of improvement, which is evaluating the Gaussian CDF at this gamma of x value. The expected improvement, so I showed you the example earlier in a previous picture. So that is a little bit more complicated, but it also only requires evaluating the Gaussian CDF and the Gaussian PDF. And there's also something called the Gaussian process lower confidence bound, which takes the mean prediction and the standard deviation of the prediction at x. And that is kind of like the example where I said earlier, you're going to look at the lower edge of this gray area to select where to evaluate next. So I actually use this particular acquisition function earlier to do this. And so the exact details of the exact equations here are not that important. So you can always look them up if you need to. But I want to give you more like an intuition of how these things actually work. And I want to start with the first acquisition function here, which is called the probability of improvement. And maybe the sampling perspective here is most intuitive, or at least somewhat intuitive. So again, we're going to draw samples from a Gaussian process. And what we want to find is, we want to find the input x star that gives the highest probability of leading to a better function value. So in order to do this, we need to compute the probability that x star leads to a better function value than the currently best one. So every time you get a better function value than this, or where the sampled function goes below the black bar, you count 1. So if you have 1,000 samples and maybe 200 of these functions are below the threshold, then you would have a probability of getting a better function value of 20%. And that is exactly what probability of improvement computes. So in a sampling perspective, you could write this down like this. So the probability of improvement acquisition function is the probability, so evaluated at x, is the probability that g of x is smaller than the best value that we have seen so far. And that's approximated by effectively counting how many functions have better function values at the corresponding input value. That is, so the delta is a 0, 1. So if it's a Kronecker delta. So if the statement inside the delta is true, you count 1, and otherwise you count 0. So if we have n samples from a posterior Gaussian process, then this would be this expression here would be the probability of x, the location x, being a better value or giving a better function value than the location where we currently have our best value. So there's potentially a bit of a problem with this thing, and you can see this here. So if we draw the probability of getting a better function value, then we would get this function here. So this is the probability of improvement acquisition function. And we will see that the peak of this is actually very close to the x best value. So it's not exactly the same value, but it's very close to this, and that is because of the smoothness assumptions that we normally make with the Gaussian process. And so what could happen with the probability of improvement acquisition function is that you only do very small step exploration. So you wouldn't make big jumps normally. So the exploration could be relatively slow. The exploration of the true function could be relatively slow with this probability of improvement. So what we could do is we could introduce some sort of slack variable, which we also know from SVMs, where we say you need to be at least a value of psi better, not like, just being better. So being better could be 10 to the minus 8 in terms of function values, but you could say we would need to be at least 0.1 or 1 better than the currently best seen function value. And that would lead to some more aggressive exploration. So the expressions will actually not change that significantly. So if we look at a minimum improvement of some value psi, then we would like to compute the probability of g of x being better than g of x best minus psi. And so this entire sum here would just add the minus psi in these expressions. And we would also get a closed form expression for the acquisition function using the Gaussian CDF. So this one is just a sampling perspective. So we can actually compute these things in closed form using the Gaussian CDF. And we just need to redefine this gamma function that we had earlier by adding this psi value in here as well. And so the acquisition function on the left is the one without the slack variable. On the right, we would add the slack variable. You can see we have this little ditch here in the middle where the improvement is insufficient. Right, so it's smaller than I'm not sure what I chose, probably 0.1. So there's no value evaluating in this area, and we would need to go a little bit further to the left or a little bit further to the right to actually get this a sufficient improvement. And that's where how you can tune the exploration a little bit more.
Please, I don't get the intuition for that little thing that we add we subtract from the epsilon.
This value here?
Yes.
Okay. So let's have a look at this this example here. Now I'm going to draw. So this is a threshold we need to cross. Yeah, so this is the best function value we have seen so far. So this is g of x best. That is the line we have to cross. What we would normally do is, for the probability of improvement, if we just look at whether function values are below this particular threshold. So for the blue function, we would be interested, maybe this is not a good color. The blue function we would have an interval that looks like this. So this is kind of the interval where the blue function is below the black line. So this interval here is gi of x is smaller than g of x best. So that's the blue function. So now the next thing is we want to find a different one, which is now gi of x is smaller than g of x best minus this variable xi. So what that means is we would effectively lower this threshold, and this value here is exactly this slack. So what the blue function now needs to do is it needs to be better than the thin black line, and now we would reduce this interval to this one here. So that is the plot we had earlier. If we have a function value, so if this is the difference with the slack variable, we would effectively cut out all input values here. So this because there are no function values in this block which are below this line, and we would also zero out everything in this area. So this is also gone, and everything in here would also be eliminated. So it's not exactly what we have plotted in the bottom, because that shows a much smaller xi variable, but it will force you to do more aggressive exploration.
This is the reason. This is why we need the epsilon to put like sort of thresholds. Mm-hmm.
Yeah. So basically, we slice out this bit from this curve to get to this curve, because the improvement is not sufficient, and then we would force more aggressive exploration than what we would have done on the left-hand side without the slack variable. So instead of just looking at the probability of improving, we can also try to quantify the amount of how much we improve. And basically, that is the expected improvement probability function. And what the expected probability of improvement function looks at is the expected value between the best function value we have seen so far and the function value that we have when we evaluate the GP, basically, or sample from the GP. That corresponding equation down here would be the closed form evaluation or closed form expression for this kind of sampling-based intuition. And if we draw, for exactly the same example that we had earlier, if you draw the expected improvement, we would get a graph that looks like this. And so we can see here that in the vicinity of the best input that we have found so far, the improvement is actually relatively low. So this one already automatically pushes you a little bit further to the left and to the right to get a better exploration and to find functions or input locations that give us higher expected improvement over the function values that we have seen as well. So similar to earlier, we can also add slack variables here to further increase the exploration. But I don't want to go into more details here. So maybe the easiest acquisition function is the lower confidence bound acquisition function. And here the idea is really to use the predictive mean and the variance of the GP for targeted exploration by means of the acquisition functions. Right? So we compute the mean minus some value, say square root kappa, times the standard deviation. So we basically look at the posterior mean prediction minus some scaled version of the standard deviation. And if that is below the threshold, then that is a good value to explore. That's what this thing means. Just look at mean minus the standard deviation, or scaled version of the standard deviation, to figure out whether we have good values for this. And the further down we go, or the further we fall below this best value that we have seen so far, the higher the acquisition function is. And that here would be the corresponding acquisition function for this example over here. So now the question is setting of kappa. How do we do this? If we set kappa to be a parameter that depends on the iteration, so how many data points we effectively have in our training set for the GP. So if we keep increasing this, the kappa, so if kappa of t, so t is the iteration, is of the order of log t, so it always gets bigger, then we are guaranteed to continue exploring without falling into a local optimum and then stopping. And then we can also get regret bounds. That means we get some statements about how close we are to the optimal value of the true G function. So these are now theoretical guarantees that we can get if we choose this particular acquisition function. We started off with a problem where we said, okay, we want to find an optimal value for a function. We want to optimize a function that is super expensive to evaluate. So we cannot afford evaluating this function 100 or maybe 1,000 or 1,000,000 times. So what we do now is we evaluate this function a few times, and then we use a proxy or surrogate model, in this case a Gaussian process, that approximates the true function. We use the Gaussian process mean and the Gaussian process variance to find out where to evaluate the true function next. And we use something that is called an acquisition function to make that decision. So we looked at probability of improvement or expected improvement or the lower confidence bound to tell us where to evaluate next. In order to do this, however, we have to find now the maximum of this acquisition function. And ideally, we need to find a global maximum. So that means in order to actually do Bayesian optimization, we have to run a global optimizer within Bayesian optimization. And the question is, why don't we just run a global optimizer directly on the true function instead of like doing all this machinery with the Gaussian process and then use the Gaussian process to evaluate these acquisition functions and then optimize these acquisition functions. So what have we actually gained? Have we gained anything? Evaluating the acquisition function is relatively cheap compared to evaluating the true objective. So imagine again, we have to pay $100 for evaluating the true objective, but we only have to wait for maybe a minute to maximize the acquisition function. So then we are happy to maximize the acquisition function. So evaluating the acquisition function requires us to make a Gaussian process prediction. But in order to optimize this, we have to evaluate it many times. But it is relatively cheap compared to optimizing the true objective function many times. And can maybe think about settings where evaluating the true objective function would require us to drill a hole into the ground to figure out whether oil is there. So that is something we do not want to do many times. So Netflix uses Bayesian optimization to find high-level metaparameters of their deep learning algorithms for movie recommendations. So these are examples where Bayesian optimization is being used, where it's very clear that you do not want to run these real experiments many times. So if doing the oil drills is super expensive and time consuming. But if you also make really bad recommendations, then you also lose customers, or Netflix would lose customers. So you really want to be careful with what you do here. AlphaGo also uses Bayesian optimization. There's actually a paper on how they use Bayesian optimization within their algorithm for finding high-level or meta parameters. So that's the reason why Bayesian optimization is actually useful in practice for all kinds of applications. Now let's move on to our final part for this lecture. I wanted to talk a little bit about limitations of Bayesian optimization, at least in a sense that we introduced it here today. One of the problems that we need to look at is that choosing the right model. So we discussed this yesterday of like how to do model selection with Gaussian processes. So finding a good covariance function or maybe a good mean function is valuable, and getting it wrong can lead to catastrophic failures. I'm going to show you an example later of like how different covariance functions can make a big difference in Bayesian optimization. One of the restrictions, I did mention this earlier as well, was that we are limited in the number of dimensions, which means the number of parameters we can optimize at the same time, and the number of evaluations of the true objective function. And I want to know whether you have some ideas of why we are limited in the number of dimensions or the number of evaluations of the true objective function. Any ideas, any suggestions? Let's maybe start with the number of evaluations of the true objective function. Why are we limited here? Assuming we wanted to use Bayesian optimization to find to train a neural network. So evaluating a neural network is really cheap. So why would that be a problem? Why does Bayesian optimization, in the way that we explained this today, why does this not scale to, let's say, 1,000 evaluations or 10,000 evaluations of the true objective function?
So you need exactly the more the number of data you have, then your covariance matrix will be larger. So when you are trying to compute it and maybe invert it, then I think.
So which covariance matrix are you talking about?
The covariance function, actually. The covariance function scales with the number of data you have.
So in the Gaussian process.
Yes.
Yeah, so that's exactly the right thing, the right way to think about this. Every evaluation of the true objective function gives us one more data point in the Gaussian process. And the limit of Gaussian processes in practice is about 10,000 data points, because otherwise we run out of RAM and we have to wait for far too long. So that means in the Bayesian optimization context, that would mean 10,000 experiments is really the limit beyond which we can't train the Gaussian process anymore without any adjustments. But it's actually even worse in Bayesian optimization. And I would even say that the 10,000 limit is something that is beyond practicality in Bayesian optimization. Even if you go to 1,000 evaluations, you are already running into huge problems in terms of compute requirements. Any ideas why that is the case? So say training is, with 1,000 data points, is definitely easily doable and doesn't take too long. But what other compute costs do we have? So one experiment equals one training data point. For the GP. So that was the first thing. So that means we are definitely need to be smaller than 10,000 experiments, just because of this. Otherwise, we can't train the GP anymore. But my claim is that 10,000 is far too much anyways for Bayesian optimization. I would say we also have to be actually below 1,000 experiments And the reason for this is, does anyone have an idea of like why that could be the case? Okay, well, there's an interesting comment. So there's because of the optimization of the acquisition function. So can you maybe clarify what you mean here? So that's definitely the right path here.
Yeah, since for each data point that we get in the pseudocode that we saw, we have to also run optimization for the acquisition function. So you can see that we have more limitation beyond just the training data points that we have for the GP.
Okay, so what does the optimizer require? So what is the compute cost for optimizing the acquisition function? What is the expensive thing here?
I think it has to do with like querying the GP for different plausible functions under the distribution.
Excellent. So this is really good, actually. So in order to optimize the acquisition function, we need to query the GP at many inputs. So that means like make predictions at many inputs. So example, if we just in a very naive way, if we wanted to find the maximum of this function, what we could do is we could, if this is the x-axis, we could define a regular grid on this axis and then query the Gaussian processor at every one of these inputs. So now let's assume we have a one-dimensional case. In 1D, we query this function maybe at 100 locations. In 2D, that would be, if you want to keep the resolution, that would be 10,000 locations. And in 3D, that would be 100 to the power of 3. So 10 to the 6 many locations. So that means we have to make a lot of predictions with the Gaussian process. So training was cubic in a number of data points, and predictions are scales here in n squared. So now the thing is, so although n squared is significantly smaller than n cubed, if we have to do a lot of these n squared predictions, that will be more expensive to actually cubic training cost. So that's the reason why I think maybe 1,000 experiments is already relatively optimistic. So optimizing the acquisition function is the computational bottleneck in Bayesian optimization. And now coming back to the first part of the question, if we look at the scalability in the number of dimensions, why can't we optimize 100 parameters with Bayesian optimization? Any suggestions? Yeah, exactly. So curse of dimensionality is a good point. Do you want to explain a little bit what that means, or what you mean by that?
Okay, so what I understand by cost of dimensionality is the larger your dimensions, the larger the number of data you will need to get a good prediction.
So yeah, maybe similar to what I mentioned earlier.
The larger parameters, the larger the number of samples you need. Yeah.
Mm-hmm. So if we have more parameters, then we would also need to run many more experiments to explore the parameter space. Yes, so if we have one parameter, maybe we can get away with 10 experiments. If we have two parameters, we optimize in a two-dimensional space. We probably need maybe a few tens, maybe 100 experiments to get some good numbers out of this. And if we get to maybe 10 dimensions, then things already a bit more problematic. But if we go to 100 or 1,000 dimensions, definitely not feasible to get some global optimum out of this. And with a lot of experiments, we again run into the computational issues of a Gaussian process, which means on the one hand, we have to optimize or train a Gaussian process, and on the other hand, we have to look at optimizing the acquisition functions. So these are the problems that we have with the GP. We already talked about different covariance functions and what kind of prior assumptions they make on the underlying function. And so these kind of assumptions now play quite an important role in Bayesian optimization as well. And so we have two examples here of covariance functions. We have the Gaussian covariance function here on the left, and we have the Matern covariance function on the right. So Gaussian, we said yesterday, the assumption is that we have an infinitely often differentiable function. And on the right-hand side, the Matern kernel says something about maybe 1 or 2 times differentiability of the underlying function. So this is a much more, the samples from this GP are much more rough than on the left-hand side. So in practice, in Bayesian optimization, it's actually more useful to have the Matern kernel instead of the Gaussian kernel, because it's a bit more flexible and adaptive. And in practice, the error bars increase a little bit faster if you go away from the training data with the Matern kernel, because your smoothness assumptions are not as strong as with the Gaussian kernel. And that leads to more exploration as well in the Bayesian optimization setting. So people have actually run a few experiments. So there is the paper by Jasper Snook from 2012 so most of these plots are actually now coming from this paper. So I mentioned early in the beginning, there was a structured support vector machine for this kind of like DNA sequence binding. And now, so Snook and colleagues now optimized the hyperparameters of this structured support vector machine using Bayesian optimization, and also used different covariance functions for Bayesian optimization. And so what they found is that they looked at 4 different types of covariance functions. So one is a squared exponential, which is the Gaussian kernel, which we have here in the green line or the green bars. We have a squared exponential. So ARD means automatic relevance determination, which has a different length scale parameter per input dimension. So it gives you a bit more flexibility. So that is the red curve. And then we have 2 Matern kernels. So one is a Matern 3.2, which is the 1 times differentiable, or the assumption of 1 times differentiable functions. And the other one is a Matern 5.2, which assumes a 2 times differentiable underlying function. And you can see that the choice of the kernel does make a big difference in terms of like how fast things go to relatively good values. In this particular case, the Gaussian covariance is a bit slower, or is significantly slower than the Matern kernels. But within the Matern kernels, it seems that maybe the super rough version of it, so the Matern 3.2, so the 1 times differentiable, is probably good in the early stages of learning, or is good in the early stages of learning, but then at some point it's being overtaken by the slightly smoother assumption in the Matern 5.2 kernel. So we looked at the marginal likelihood surface yesterday, and you saw that the marginal likelihood surface can have multiple local optima. And that is definitely true when we have relatively small data sets, because when we have small data sets, then we have multiple explanations of the data that make all sense. And then picking a single explanation could be a really bad idea. And we do definitely start with relatively small data sets in Bayesian optimization. And so then maximizing the marginal likelihood can be a really bad idea. So what we can do is we can start thinking about integrating out the Gaussian process hyperparameters using sampling methods such as size sampling, so Markov chain Monte Carlo sampling. And an example of that would be size sampling to integrate out the hyperparameters. This is relatively expensive, but if it comes to reducing the number of experiments that we have to run on the real system, where we have to pay a lot of money for, then it's probably worthwhile spending some more compute time on doing a proper Gaussian process modeling and integrate out the hyperparameters. So what we would then look at is the integrated acquisition function. So previously we just called it alpha of x, but implicitly it was always conditioned on the Gaussian process hyperparameters. So what we could now do is we can average over all hyperparameters according to the posterior distribution or distribution on the hyperparameters. And so if we sample from this posterior distribution, we can compute this expected value here as a Monte Carlo estimate. So 1 over capital K times the sum over small k equals 1 to capital K of alpha of x, and then evaluated at theta k, where theta k is a sample from the posterior distribution of the hyperparameters. Again, they did run a few experiments with the example of online LDA, so this topic modeling that we had as a motivating example early on. And they looked at 2 critical hyperparameters that control the learning rate. And these hyperparameters are now learned by Bayesian optimization. The idea was to minimize an objective that is related to topic modeling. So they have 3 methods that they look at. They look at random grid search. So basically sample these 2 hyperparameters randomly in a hypercube and then evaluate LDA on this. And that would be the black curve. That actually works relatively well. If you optimize the GP hyperparameters and use the expected improvement acquisition function, you would get the red curve. And if you integrate out the hyperparameters with MCMC and use the expected improvement method, you can get the blue curve. And I think the important thing here is that the blue curve is so much faster in the early stages of learning. So we're going to get to a relatively good place after maybe 10, maybe 20 iterations. And then it kind of gets the same numbers out as the optimization method, Bayesian optimization, where we optimize the hyperparameters. So maybe key message from here is that especially in the early stages of Bayesian optimization, it's definitely worthwhile integrating out the hyperparameters because you get faster learning rates. Towards the end, I would like to maybe show you some examples that's more closely related to robotics. And here's an example where the researchers were inspired by running dogs where the dog had lost one of the legs. So this dog only has 3 legs, and the dog apparently managed to run around and play with balls more or less in the same way that they did before they had the amputation. So they now took a robot. This is a robot with 6 legs, and they broke a leg. Yeah, so they removed bits and pieces of one leg. You can see this here on the right-hand side. This leg is broken, and they wanted to learn now a controller that makes the robot walk despite the broken leg. And they use Bayesian optimization for exactly this for this purpose. And what they found out that after only 3 trials, the robot could compensate for this broken leg and kind of replace this broken leg by just using the other 5 legs in a slightly different way. And so what we see here in figure D is the velocity of the robot, and we can see that after over 3 trials, the speed of the robot significantly improved, right? So we're going to get from 10 centimeters per second to 22 centimeters per second to 30 centimeters per second. So that is only with 3 experiments. Slightly different example was an example that I was involved in a few years ago. So this is a walking robot, a bipedal robot. So it has 2 legs, and it has 4 motors. So 2 motors are in the hips. So there's no torso. It's just the lower part of a humanoid robot. It has 2 motors in the hips that control the left leg and the right leg. and 2 motors in the corresponding knees. And what we wanted to do is we wanted to optimize the controller parameters. There were 8 parameters in order to make the robot walk fast and also reliably. So what we first did was Roberto Calandra, who's the first author of this paper, he spent a few weeks in the Robo Lab, and he did what we said earlier is like manual tuning, right? So in an 8-dimensional parameter space, he ran a lot of experiments, and this parameter setting doesn't work. Let's increase this parameter a little bit, then decrease this one a little bit. And then after 2 weeks, this robot was kind of like limping without falling over, at least not for a few seconds. And that was like the end of like, where Roberto then said, I'm not doing robotics anymore. This is too much work. And then we came across Bayesian optimization and said, okay, let's try this out. So we ran Bayesian optimization on this setting, where in this setting, the input to the black box were these 8 parameters that we wanted to optimize. And the utility that we wanted to optimize was the distance the robot walks in 10 or 12 seconds. So to measure this, we effectively just took a tape measure and measured how far the robot walked. And that is why this entire thing is a black box. It's just totally unclear how these controller parameters translate into the distance walked. We found good parameters after about 80 to 100 experiments. And we could do these 100 experiments in about 6 hours. So that means compared to the 2 weeks that we had before for finding these controller parameters through manual tuning, we achieved a really substantial speed up by breaking this down to something you can actually do in half a day or maybe a day. And I wanted to show you a short video of like what this looks like in practice. This is how it works in this example. So we wanted to find these good walking parameters, and we used Bayesian optimization to automate the process of finding these parameters. And in the early stages of learning, we can see something like this. Right, so the robot does like one step and then falls over. And after about maybe 20 experiments, we got something that looked like this. So it's a bit wobbly and unclear, and then it falls. This kind of like falling is that it's one of the reasons why you do not want to run too many experiments, because the hardware will break at some point. And then you have to replace parts, and then the mechanics of your robot change, and then you have to basically start from scratch. But after we ran Bayesian optimization for a bit longer, we got to a walking behavior that looked like this. So the robot was relatively fast and was walking for 2 or 3 minutes without falling. So that was really motivating for us. And I just really, as an example for when Bayesian optimization is useful, I thought that would be nice to show. So in robotics, it's also really useful. It's not only good for AlphaGo or other things, but also in practical applications. And here's some comparisons of like where we investigated different optimization strategies and different acquisition functions. But we did some very naive things. So we used the Gaussian kernel, we optimized the hyperparameters instead of like integrating them out. But it still works. Okay. So there are also lots of topics that we didn't discuss today. So, but here are some links to corresponding research. There is something about entropy-based acquisition functions where you describe the distribution over the best input location instead of like finding a distribution on the best function value. So looking directly at the X values. Looking at Bayesian optimization that does look ahead, so looking multiple steps ahead instead of like optimizing for the next best experiment to run. You want to look at the next maybe 3, 4, 5 experiments to run. There is research on high-dimensional Bayesian optimization for example, through embeddings of high dimensions into lower dimensional spaces. Frank Hutter in Freiburg has a lot of work on large-scale Bayesian optimization. So that means also other ways of hybrid problems where some of the parameters are discrete, some of them are continuous, but then also work in 70, 80 dimensional problems. Then there's work on efficiently optimizing acquisition functions. So instead of having a grid, what you can do is you can randomly sample maybe 10,000 points in your parameter space and then run a local gradient descent from each of these points to find the best value of the acquisition function. So if you're interested in this kind of work, then please have a look at this paper here. There is work on using non-Gaussian processes for Bayesian optimization, for example, random forests or Bayesian neural networks. Bayesian optimization with constraints. So it's basically constraint optimization within Bayesian optimization. Then there's this work on automated machine learning, which is I think a slightly bigger area than Bayesian optimization. And then there is, again, something like multitasking, parallelizing, Bayesian optimization, resource allocation. There's also a lot of work on that. So software is also around. So if you want to have a look at this, it's, whether you use Torch, Python, MATLAB, there must be R toolboxes as well. So there's a lot of stuff around if you want to play around with this. So to summarize this, we wanted to look at global optimization of black box functions, which are expensive to evaluate. And this was motivated by some meta challenges in machine learning or AutoML, for example, protein folding or AlphaGo, or maybe in robotics. And really the key idea was to use a probabilistic proxy model that is cheap to evaluate and use this proxy model to suggest next experiments. We looked at the acquisition functions in some more detail, which tells us where to evaluate next. And one of the key properties of the acquisition function is, or the key jobs that it has to do is, it has to trade off exploration and exploitation to ensure that we do not end up in a local optimum.